So good morning, everybody. I'm gonna start. Thank the organizer for this very nice conference. And I'm here today to present you some result of the ALMA large program I've been leading for 5 years, and which finally, with very difficult data processing, managed to give very nice results. At least I think this way. So I'm indebted with people in my team, especially the PIs. Co-PIs around me are Adam Ginsburg, Fabien Louvet, and Patricio Sanueza. And the members of the management team, Timia Shengarid, Sylvain Bontin, Roberto Galvan Madrid, Amy Stutz, and Fubitaka Nakamura. The ALMA-IMF large program is actually constituted of 70 members, or maybe even more, I think now, from 11 countries, a lot of PhD and postdocs, which are doing the most of the work. Half of the members are from Europe. A lot of them are actually from France. We have also members from America, North, South, and Center, from Chile, and from East Asia. The work was initiated with a pilot program, which was supported by the Programme National PCMI and PNPS. And now we are getting money mostly from, in France, actually from the EcoGal Synergy program of Patrick and Bell, who presented earlier this week, and from the Cosmic ENR program. So, yeah, so the outline of my talk is going to be just a first presentation of the an introduction about the initial mass function and its origin, because it's the main focus of this large program. And then giving you an idea of what are the targets that we are observing, and then giving some results on the core mass function, but not only. To start with the science, I would say that for long we've been believing that the IMF, so the mass function of stars arriving on the main sequence, would be universal. So we have here a presentation of what would be the form of the IMF, constrained by observation from the local neighborhood, so around our sun and in nearby clusters, young stars mostly. So you have an IMF, which is represented in this shape, the number of stars as function of a stellar mass, which is a log normal function, which is peaking around 0.3 solar mass, plus a power law in the massive regime. So as I said before, there have been some claim in the past that the IMF might not be so universal, but these claims are getting more and more important these days. And we have some kind of proof that in the starburst clusters, in the massive young clusters in our galaxy, in nearby galaxies, and even in the very nearby massive star-forming region, which are around 1.4 kiloparsec, that this is not totally true, and that the massive regime could be even flatter. So it's why we call them top-heavy IMF. So having more massive stars than we believed from this shape of the IMF. Now, let's come back to topics which is more important for the PCMI, which is the cloud itself and the structuration into cores. So we've been studying cores using simulated ground-based observations, for example, from the IRAM 30-meter, using Herschel images and near-infrared extension. And all these surveys have been extracting cores first, and then building core mass functions that are the equivalent of the IMF, but for cores. So you have graphs like these ones with the number of cores as a function of their mass. And you have two examples here, one from the ROF cluster and another from the Aquila cluster. This is from the ground-based observation. That's the first study that's shown this kind of similarity between the CMF shape and the IMF. And this is a study which done much more than what we did at the time with much larger statistics. And that showed that the CMF shape was resembling the IMF. So all these studies, and there have been really a lot for 2 decades, showing that there could be a one-to-one relationship between the core mass function, I'm going to say CMF in the future, and IMF, was leading to a very simple conclusion, saying that, okay, the IMF could be determined at the fragmentation stage of the cloud formation, and that these cores that are forming into the clouds are going to be the direct progenitors of the stars. But, and there is a big but here, studies that have been done during these 2 decades were focused on the global clouds, which are the nearby cloud for us, those that are between 100 and 500 parsec from us. And they are not at all forming, first of all, massive stars. So they are focusing on low mass stars only, low mass star precursor. And they are corresponding also to regions which are not typical for the main mode of star formation in the galactic disk. When you are around our sun, we are not in the galactic arm, so it's not the main mode, most probably. So we needed to go further. And I wanted before to mention what are the main assumptions that we are making when we compare abruptly the CMF and the IMF. First of all, we assume that the core that we are detecting is really well defined and that its mass is corresponding to the total mass of the reservoir of gas which is going to be used to form a star. So we are, first of all, neglecting the gas mass feeding, which we know are really everywhere in the cloud. From simulations and observation, we really see a connection from the large scale to the small scales through this feeding. We're also assuming that the core is going to have to fragment during its star formation activity, star formation process, and that multiplicity is going to be homogeneous for the cores, even if there are 0.1 solar mass cores to 100 solar mass cores. The other thing we are assuming is that we have a uniform gas to star mass conversion. This epsilon I didn't mention actually. This epsilon is the efficiency which is allowing the CMF to go back to the IMF with some efficiency of transfer of the gas of the core into the star. So this epsilon is supposed to be rather constant if we are assuming that it's outflows which are setting this epsilon. But in fact, in observation and simulations again, this epsilon is observed to be varying with density, being low when the core is low density and high, and could be even around 100% for very dense cores. So the other assumption that we are making, and it's not the last one most probably, is that the lifetime of the core is going to be independent of its mass, meaning that when we observe a core mass function, it's at a certain time, and it's probably corresponding to a process of a star formation event of 10 to the 5 years, let's say the collapse phase. And that in the end, these cores are not going to be stand here for longer time if they are low mass or rather than higher mass. So all these effects should be actually cancelling out if we really have to have these shapes between the CMF and IMF, which are so similar. So either we could think that there is some kind of conspiracy which are cancelling out all these effects, and it's called the central limit theorem, where you have several physical processes which are independent, which are leading to this log normal shape. Doesn't tell you anything about the power law tail for the CMF. And the other more logical thing is that our uncertainty in observations are not allowing us to see variations of the core mass function. So we wanted to go forward, and we wanted to stop to take for granted that this CMF and IMF, which are prescription of the star formation activity, are universal. And then we also wanted to think more deeply that what we call core, which are in fact peaks in our images, are not exactly the gas reservoir, which are going to be used for the protostellar collapse. Patrick mentioned resolution issues. If you have higher resolution images, you're going to define cores differently. But there is also this idea that the cloud is actually multifractal, and you have a relation between the large scale and the small scales, and it's even more stringent when you have dynamical environments. You really have flows going from the moving mass from the large scale to the small scales. So for observers, in fact, the main difficulties we had at the time was that we were limited to observation really around us. And that's a difficulty in that case to use what we observed there and extrapolate that to the Milky Way or even to the whole universe. Actually, we should not make that. And that's the reason why we end up proposing a program with ALMA to go one step further in our galaxy to get something more realistic for the relation of the CMF and the IMF. So I then come up to my second point. What are these ALMA-IMF clusters? The objective was, in fact, to focus on the gas-dominated phase of protoclusters, because with ALMA we won't be able to observe the region which are really which are more stellar, like most closer to the star activity, let's say, which are mostly composed of stars, let's say. So, but we wanted to have some different evolutionary stages. Since we wanted to have star clusters, we focused on parsec-sized clouds, and the most massive to have rich protoclusters. We also wanted to have access to cores. So the resolution we aimed to was about 2000 AU, which could be said the size of the cores. And the sensitivity around 0.2 solar mass to really go beyond this turnover of the CMF, potentially. So it all started from the survey of Timia Shengri using Atlas Gal, and she made a catalog of 200 most massive clumps. And we made some filter on this catalog, filter and distance, because we wanted to be able to map with ALMA mosaics which are not too large but covering parsec scale, and we wanted to have the enough resolution to get access to the course. So the filter we had was between 2 and 5.5 kiloparsec. Then we made a filter in the flux, 2 of the most massive objects, and we came back to the images themselves. It was the work of Célin and Bontemps to select the most massive clouds associated with this Atlas gas clump, because we didn't want to have one single object inside nothing. We wanted to have large mosaics and then rich protoclusters. We also rebalanced the sample between what we call infrared quiet and infrared bright, and I will just talk you about on the next slide. And we end up with 15 of the richest protocluster cloud in our nearby environment. So the criteria we used to set up the original stage of ALMA-IMF protoclusters, there are several, but they are, well, it's not complex, it's not direct, the observation and the classification. So the first one is the easiest one. We use the gas heating that can be traced by mini-infrared fluxes of Spitzer, going from a quiet region to a bright region, depending on the intensity of the flux of Spitzer. And then we used also the ionized gas, which by chance could be traced by the ALMA data. We used first 1 to 3 millimeter flux ratio that allowed to separate thermal dust associated with filaments, cores, and so on from free emission associated with H2 region. And we also use the H41 alpha recommendation lines that we have in our data, and that allows really to pick the free emission here and there associated with ultra-compact H2 region with extended H2 regions. By doing so, we managed to get access to young region associated with only dust filaments, intermediate regions that were having dust filaments plus the appearance of a few ultra-compact H2 region, and evolved region which were really embedded into developed H2 regions. We also used the ratio of protostars versus prestellar cores in our samples to define some burst regime. In fact, in some places, we had some enhancements of this ratio, and we could even say that some region could be pre-burst and post-burst region are those which are with the H2 region just forming now. So here are some images for you to better understand our selection process. First of all, you have in contours here, white contours, that's the Laboca 870 micron images. And what you can see is that these regions here are really the densest, and that's the reason why we focus on these so-called regions. And you have one region here, which is infrared quiet, but also young, because associated mostly with filaments, which are seen here in orange. And when you have some blue patches like this one, it's strong free emission. Here it's an ultra-compact H2 region. And you have also some filaments, so we call it an intermediate region. So then we end up having 15 clouds separated between 6 youngs, 5 intermediate, and 4 evolved. And they are having some masses, total mass imaged by ALMA between 2,000 to 20,000 solar mass. And they are covering a few parsec square. And what can I say more? It's about it. They are covering in total something like 50 parsec square. So these are where are they located in our galaxy? As I said you before, we were for long observing things which are the global clouds located in this relative void in our galaxy, while we were interested in having a better view of what's happening in the main mode of star formation in galaxies in general and in our galaxy specifically. So the ALMA-IMF clouds are in fact these greenish disks here that more or less lie on the scutum centrus arm and that could be tracing better, be more representative of what are the star forming clouds in the Milky Way. So we end up also stopping at this position, which is the tip of the galactic bar, because we didn't want to be able to spend too much time to be sensitive with ALMA, for example, and have a very high angular resolution. So we in that case, we really have 15 clouds which are paving different evolution stages, and that could help us understand better the core mass functions. So that the database itself is composed of 12-meter SEA and total powers to really have all the structure in our cloud. We wanted to have a 2000 AU resolution and 0.2 solar mass sensitivity. The area that we are covering is about 50 parsec square, and it means mosaics of a given with multiple fields, let's say. And the data reduction, which has been done, was pretty long because we had to recalibrate all the line cubes. And the 12-meter, actually it was done by the ARC, but we started this process and we pushed them very hard to make that. And there was also so a lot of work done in the pipeline to self-calibrate the continuum and have a much better sensitivity. All this work has been led by Adam Gainsbourg and Nicole Cunningham. And there is a paper which is already submitted for the continuum, and one which is submitted now for the lines. So now let's go on the science itself. We organize our work, and I'm not going to ask you to read all that, on 3 specific scientific working groups. The first one focuses on cores, and we are not just working on the core mass function, but also on the protostars. Another one working on the hot core and chemical enrichment, led by Tibesh. This one is led by Tomanoni. So we worked for the moment on the protostars themselves, and we're gonna work on the outflow, creating some hot cores as well. Then some complex organic molecules, not some hot cores. And there is a kinematic working group which is now working more efficiently because the data sets are ready, and which are going to work on the turbulence, on the rotation in flow, filaments, and so on, led by Imich Stutz and Manuel Fernandez-Lopez. So let's come to the few results that we got on the core mass function. That's one obtained actually from the pilot study of that we done with 1 millimeter detail only at the beginning. Here is an image of the protocluster that you can see, and all these circle here, ellipses actually are cores we extracted with the software called Get Sources, and they range 1 to 100 solar mass. So we really have the ability to trace what's happening for the high mass regime in this region. So what we obtain in terms of core mass function is what you have here, still the number of cores as a function of the mass. And we did a lot of work in defining the uncertainty in this curve, which is actually this histogram, blue histogram shown here. But what is sure is that this part from the completeness limit down to 100 solar mass is much flatter than what was observed for previous CMF and what was observed for the IMF itself. So either we have in this region something special, and we're going to have an IMF which is going to be top heavy itself as well, or we're going to have a core mass function evolution, which is going to be different from one step to another, and could be a complex relationship between the CMF and the IMF. I should say that there was also at the time one study that really showed that on single protoclusters, and there are other studies with various angular resolution and accumulating several clusters. So Fabien Louvet took in charge the complete core population study in the clouds to build some core mass function. So here are 3 of these regions where you extract some cores. He used for that what we call the line-free continuum images, using 1 millimeter and 3 meter, and smooth them to the same physical resolution to really be able to compare. My God. Sorry. So we have a catalog of 700 cores. And what we obtained was that there is an evolution of the CMF going from still top heavy when you take all of them, top heavy when you take the young and intermediate regions, to something more closer to the canonical IMF when you go to the more evolved region that we have. So there could be some CMF evolution time. So I'm gonna be very faster on this one now. That's a work led by Johan Puto. We managed to separate one single region into pre-burst, burst, and post-burst subregion, as I said to you before. And we tried to compare the CMFs that we were obtaining. So some were really flat, the burst-like regions were having flat CMF. And when you go to pre-burst region like this one, we get something which is getting closer to what was observed, for example, for Aquila and the Salpeter slope. And what is interesting is that we try to make some correlation with plenty of things like the mass of the regions, the medium density, and so on. Nothing was really helpful except for the PDF, so the probability density distribution, which is shown here. So in practice, the number of pixels at a certain column density as a function of the column density. So this is the column density images that we had. And if you forget everything which is there, which is not traced properly by ALMA, you get something which is flat for the pre-burst regime, but much flatter for the burst regime. So there is something that led us to the sketch which is shown here, where we thought that the molecular cloud could be like this one, having a PDF which is log normal plus a tail associated with the filaments and the core. But then it could entering the pre-burst, main burst, and post-burst regime, where you had something even flatter for the PDF, and the CMF would react this way. At the beginning, you have something which is, let's say, typical for Salpeter with a Salpeter slope at the end, and then something which is top-heavy when you enter the main burst, and you have the same top-heavy shape, but bottom light CMF when you enter the post-burst, and that's probably due to the effect of stellar feedback. So some more studies have been done for the hot core studies. Mélis Bonfin found 65 hot cores in our fields, and there are questions about the low mass cores that are associated with these hot corinos. Are they different in nature, or are they the same? In fact, they have a molecular complexity that could be more or less similar. That's a very nice result obtained by Nathalie Bourrier and his collaborators, showing that if you scale all the spectrum of here 7 hot core from the same region, you obtain variations in intensity of line, but not by large factors, something a factor of 2 to 3. So it means that you may have some kind of homogeneity in the molecular content, at least in one single region. And that can tell you that maybe it's just the amount of gas which is heated, which is making the strength of the line, and not the different content of the molecules. So I'm sorry, but these are outflows surveys that are being done. And you could see that these outflows are showing some structure which could be associated with the protocellular activity. And there are some kinematical studies that are done using N2H+, using ACA and 12-meter data sets. And there are some insight on the rotation on inflow from large scale to small scales. Something done by Amy Stutz and Manuel Fernandez Lopez. And last, we've tried also to get the best tracer to trace the cores themselves. And it was really difficult because, in fact, the best tracer we have in our hand for the moment is DCN. It's actually tracing only half of the cores, not the very low mass, neither the very massive, because, in fact, they are optically thick. So it means that, well, that's for only associated with the data release of the data cubes, but we need really to combine all these traces. And I'm gonna finish here. Thanks a lot.